Hello, my name is Yumeka, and today I'm going to talk about fault resilience of reinforcement-based satellite autonomous task scheduling. And the problem we are looking at is agile Earth observing satellite scheduling problem. And Earth observing satellite is satellite with imaging instrument to collect target data, and scheduling problem's goal is to find the best action to maximize the reward for image target. And agile is, as you can see from the figure, the satellite can maneuver along and across the orbital path. And the agile satellite can increase the opportunity to take one image, but it makes the problem hard to solve. So I'm going to talk about the way we solve this problem using reinforcement learning, as well as how we can incorporate this problem with faults. But why we need to consider fault? Because traditionally, if satellite experience some kind of fault, then it enters safe mode and lose opportunity for imaging. So in this research, I will investigate if the reinforcement learning policy can be more resilient for faults. And related work is focusing on fault identification using machine learning, and not many research is going on like after fault action. So, and some did, but not related to scheduling problem. That's why we are investigating the fault resilience for scheduling problem. As for the formulation for this problem, we use POMDP, partially observable Markov decision process. For the sake of time, I'm not dive into detail of the POMDP, but for the formulation as a state space, we consider all information to propagate the simulation forward. That includes all the satellite state and also environment states. And for the action space, it is 34 actions in total, and it includes 32 upcoming target imaging action, as well as charging and desaturation of reaction Hoyle action. For the reward, this is sum of all the targeted image, and if the target is already imaged, there's no additional target for the duplicated image. And finally, observation. This is a state that are used for decision making, includes reinforced reaction Hoyle speed. That is a part of state space. And for algorithm, we use reinforcement learning, and this is a framework for that. So basically, we train agent or policy to decide best action concerning the current observation and reward by interacting the environment. And to train the policy, we use reinforcement learning with neural networks, so deep reinforcement learning. And for the algorithm, we use asynchronous PPO in RLlib to make it possible for reinforcement learning for scheduling problem. Our lab has developed BSK-RL, and you can go to the website by using this QR code. And this is equal to Basilisk plus Gymnasium. Basilisk is a high fidelity and fast spacecraft simulation framework. This is also the framework our lab has developed. And also the Gymnasium is a reinforcement learning interface that widely used. Combining those two, we are enabled to make the reinforcement learning environment for scheduling problem. And this is really fast simulation using Basilisk, as well as this enable us to do the fast evaluation after training, so that it's really good for real-time application. And for the training and testing, we only consider a single satellite operation for now, and circular orbit with a period of 95 minutes, and also I consider 4 reaction Hoyles with this configuration, and 3 of them are aligned with the principal axis of the satellite, and the redundant Hoyle is tilted evenly to the 3. For the training, we train the policy without fault, so that policy hasn't experienced the fault during training, and we consider one episode as 3 orbits. That's the one terminal state, and there are 2 different terminal states as well. This is considered as failure when battery goes to 0 or reaction Hoyle speed exceeds maximum limit. As for testing, we test the nominal case policy in fault environment with shield to prevent the agent from taking actions that could lead to failure, so that when the battery or reaction coil speed exceeds some threshold, then we force them to take recharging action or the desaturation action. And finally, fault occurred at the beginning of each episode. And we tested 5 different fault types. First one is individual reaction coil fault. When the reaction coil is not controllable, it is possible to rotate but not controllable. And second one is power limit, reducing the maximum power due to reaction coil. And third one is friction increase, increasing Coulomb friction torque. This is constant regardless of reaction coil speed. And fourth one is measurement fault. This is an encoder measurement turns off or stuck at the current value. And finally, battery capacity fault. This is actual battery capacity is reduced compared to the nominal case. And first result will be the individual reaction coil fault. And this left plot showing the reward compared to nominal case scenario over the request, which is the number of targets. And this plot showing the image success ratio. This is the number of success image over the satellite attempt to take the image action. And you can see the big correlation between those two plots. And finally, aliveness. So when if satellite experienced failure, they couldn't go to the 3 orbit, so that how many satellite could survive whole 3 orbit or when it died. This is also compared to the nominal case scenario. And from those figures, you can see that across and along track maneuver have significantly important impact on performance because most action failed. Not only imaging action, but also charging action. That's why both reward and also aliveness decrease a lot. And for the reaction coil 3, this affects less than 1 and 2, but still have serious impact on performance, but not much impact on aliveness. And finally, reaction 4 is kind of between those two cases. And as you can see from this figure, reaction coil 1 have the most impact, so that I'm focusing on reaction coil 1 fault for the different types of fault. And the first one will be power limit fault, and we reduce the maximum power draw to 0.01 to 10 watt. And there is torque limit as a default, but there is no such a limit for power draw. And this is a reward plot, and as you can see from figure, the performance is gradually decreased as the battery limit decreases. This leads to slower movement and increasing the frequency of image action failure. That's why you can see the gradual decrease of performance. As for the aliveness, you can see the huge gap between 0.1 watt and 0.01 watt. This is because those cases like 0.1 watt or above cases, those cases slow maneuver to image but still fast enough to recharge. That's why you can see the huge gap between those. And for the final result will be friction fault. Increase the Coulomb friction torque. The default value is 0.5 millimeter, but multiply it by 10 to 1,000 for faults. And this reward plot showing the gradual decrease of the performance for multiply at 10 to 300, but you can see the huge gap between 300 and 400. But why it happened? So you can see the aliveness plot, and you can see the huge gap for 300 between 300 and 400. Why it died for a lot for 400 cases? So when you're looking at the just failure cases and just looking at when it dies, then 400 and 1,000 cases, more than 80% of those cases died in eclipse. So we can say that by increasing friction, it leads to higher power consumption that lead charging become insufficient during eclipse. That's why you can see the huge gap for the performance as well as the aliveness. So as for the conclusion, we evaluated the fault resilience of reinforcement learning-based policy for satellite scheduling, focusing on reaction-free faults, and we observed a gradual performance decline as fault severity increased with clear threshold for safety aspect, and we see the critical need for resilient policies to address fault. So that's why my future work will be how to make the policy more resilient to fault. And also we can explore different types of fault as well. And thank you for listening. And if you have any question, feel free to reach out to me, or you can go to the ABS website as well as BSKRL and Basilix website. Thank you so much.